Okay. So the title of the talk here, Faster, Bigger, Better Science with MVAPICH. So this talk will have a similar theme to the talk I've given the last couple of years here, which has gone over pretty well. There are really 2 points that I want to make in this talk. One is that I would like to show some of the science that Livermore is doing using the MVAPICH software package. Right? And I think that's important. I know that the team developing MVAPICH puts a lot of time and effort into it. But it's middleware, and I don't know if you have a full appreciation of the great things that people are able to do using your software. And so I want to try to complete that cycle a little bit and show you some of that. The second point is some features and capabilities that we think we'll need from MVAPICH going forward to continue doing science. Right? So 2 points, what are we doing with MVAPICH today? And the second point, what do we need from MVAPICH in the future? There's actually a hidden third point in here that's pretty subtle. I'll see if you pick it up by the end of the talk. Normally, I would like to open up with a joke, but I'm lousy at writing jokes. But I do have a slide that I think will win over the audience here instead. So, unless you're working go Buckeyes! Did anybody get to go to that game here? How many people watched it at least? All right, that's good. I was lucky enough to get to go to the game. That was actually from my seat. This is also from my seat. This is the team running out on the field. And there are 2 things that I want to point out here. First of all, there's a missing O. I don't know if they show that on television or not. Second of all, you can see this is all scarlet on this side, which means that my seat is in the middle of the Oregon alumni fan base. So here I am, Ohio State fan, dressed like this, buried in the Oregon fans, and the first thing I have to do is explain why we can't spell Ohio. So it's kind of a rough start to the game, right?
Did you have to explain the pants?
The pants are wrong. They took one look at me like, okay, I understand that. But so it's a rough start to the game until this play of the game, which is my favorite play of the whole game. Right? And this is Zeke Elliott at the end of the third quarter. Oregon had just come back to get within 20 to 21. Right? So the Oregon fans are starting to get cocky again. Until Zeke runs this play at the end of the third quarter. He takes out left, cuts it upfield, drags one defender about 5 yards, spins, knocks another defender into the end zone for a touchdown. Buckeyes take a lead. The Oregon fans were so deflated, they just could not stop Zeke the whole game. Or at least I thought that was Zeke. Right? It turns out that it's not who you think it was. And you can see this in the reverse angle of the same shot. Here's who actually ran in that touchdown. So I knew Dr. Panda was a big fan, but I was really surprised to see him on the field padded up, knocking over Oregon players. I'm like, well, what has got Dr. Panda so motivated to run over 2 kids from Oregon for a touchdown? And I noticed on this Oregon Ducks uniform, just below the duck, there's a little blue diamond there. And when I blew that up, I zoomed in on that, it suddenly made sense where Dr. Panda would knock over 2 kids from Oregon to score this touchdown. Touchdown Buckeyes. Okay, so on to the talk here. So who is Livermore and what do we do? We have a number of different missions we're responsible for. Right? Biosecurity, counterterrorism, defense, energy, intelligence, non-proliferation, science, and weapons. These are all the official missions actually pulled from the website. The main one, of course, is we're responsible for maintaining the stockpile of the nation's nuclear weapons. Right? And for all of these missions, we're very heavy users of HPC. So these are the systems that we currently have. The open side is at the top and the closed side is at the bottom. The machine names are on the far left, and the speed of the system based on wind pack is over here on the right. And then these are color-coded sort of based on how we use the system, right? And so the pink ones are what we call our capability machines. These are our very big systems for which we only allow a few users to run, but they tend to run and use the whole machine at one time. Right, so those are where most of the flops are, but really relatively few jobs run on those systems. far more jobs run on the orange systems. These are the capacity machines. So far more users are using these, they're running smaller jobs. Right? They're still fairly big systems. You can see some of these have 20,000, 50,000 cores. So they're not really small, but this is where most of the jobs are running. Then we have some viz machines. These are to visualize, post-process the data we get from the simulations. These are always loaded down with GPUs. And then we have some serial clusters where people run single node MPI jobs. So that's a breakdown by the machine type, but if you look at what we're using in MVAPICH on, it's the majority of the machines. In fact, it's the majority of the machines that most of the people are running. Right? So we're very heavily dependent on MVAPICH. So why do we go with MVAPICH? Livermore was one of the first labs to build large-scale infinite clusters, and at the time, MVAPICH was really the only MPI library available. Right? So right out of the gate, we're MVAPICH users. But we could only do that because MVAPICH was fast, scalable, and reliable. Right? If that didn't exist, we couldn't build these systems to begin with. It's still today even the fastest for many of our users. And the other reasons is that we've always had good connections back to Ohio State. Right? So they've always been very willing to work with us to fix bugs as we come across them. Part of the reason we have these good connections is the summer interns that we bring out each year. Right? We've had a very good internship program, and I would recommend any labs or other industry in here, if you can bring out students for the summer or any time of year, I'd highly recommend doing that. Right? You build a very good relationship with a student, also with the MVAPICH team, and that relationship lasts not just through the summer, but basically that student's whole career. Right? So you form these very good friendships. And you also actually get very high quality work for the summer that you bring out. Now, I made the joke last year that each successive student that we brought out had to have a longer name than the student before. Right? So if you go down for math or IU, you can see that. And yeah, so sort of broke the trend this year. So right off the bat, we were disappointed with Sorov's performance. But I thought of a way to remedy that, so I came up with a nickname that he hasn't heard yet. So, Sorov, the best dressed coder from Columbus, Chalkboard. Right? So now he has the longest name, and you can see from the picture he's clearly the best dressed. Now, to be fair, I didn't give these other guys warning, including Ari, that we were going to take their picture. But, you know, Sorov, he's definitely got more style than I do. All right, so now let me get on to a couple of examples of the science. First of all, some background on the National Ignition Facility. If you can make it out to Livermore, I believe they run public tours of this, and I would highly recommend doing that if you can get out there. This thing is just amazing. So this complex houses the world's highest energy laser. It's in a building that's the size of 3 football fields. Right, so it's a giant facility. Football fields aren't really on top of the building, which I was disappointed to find out. Inside that building are these laser bays, right? So it's a little tough to pick out probably from this picture, but you can see these gray tubes. It runs the length of rather than the width of the building. Every one of those tubes holds a laser. So there's a master oscillator in the building that has one laser pulse. The pulse gets split into 192 beams and then amplified as it runs back and forth through these tubes. To give you an idea of the scale of this, it's elevated up off the ground, that's the person walking down below. So this is just a massive facility. Eventually these beams all get routed through bouncing off mirrors to this target chamber, right? Which is shown in the blue. It's kind of hard to see because it's buried behind all this equipment. On the right you can see a little bit better, but there's this giant blue ball. That's the target chamber. That thing alone is 30 feet high. Right? So this is somebody inside of that ball working on the arm that holds the target. Oh, yeah.
What's the length of the last post?
Good question. I've got a slide that has it in nanoseconds.
Okay.
So if you can figure out, just multiply the speed of light. But at the end of that target arm, this is what the target looks like, right? So this lady is looking at it. It's the size of a pencil eraser. Zoom in a little closer. We call this thing a hohlraum. It's a gold cylinder. It's actually made out of gold. that's important for the laser beam. Inside of that is a frozen BB-sized ball of hydrogen. Okay, so there's some hydrogen, they've encapsulated it into a plastic ball. That sits inside this little hohlraum. And then finally, when the lasers come in, it's ultraviolet light, it hits the gold, that produces X-rays. The X-rays heat the plastic shell on that hydrogen. The plastic starts firing off, which then equal opposite reaction compresses the fuel. Right? And then finally, you get ignition. Or at least that's how it should work in theory. We're not quite there yet. Okay. So what's going on at the moment, and here's actually how long the laser pulse lasts. So it's 20 milliseconds. But what's happening, or what happened for a long time, was that it turns out that plastic shell was getting mixed in with the hydrogen fuel, and that was preventing a good fusion reaction. And so people started thinking about how to solve that problem, and somebody came up with the idea of reshaping the laser pulse. And so they went from this black laser pulse to the red laser pulse. And then they started modeling. This all was done in MVAPICH. And so at the top here, you can see this is the old laser pulse. You can see sort of these fingers coming off. And then here's more severe mixing. Right? And as they changed that laser pulse, the compression got better and better. And this is actually coming out from MVAPICH. So MVAPICH backed up the theory that somebody had that if they changed the pulse, they could get better reactions. And again, here's another example of how well the simulations are actually matching up with real measurements. Right? So this is the simulated yield. This is the measured yield. And what you want is a nice straight line here. And all of these guys are for the most part, following these lines. Right? We're evidence that the simulations are matching up here. So, and then the end result is over here. So this is the exciting metadata. So this is the years down here. This is 2011. And about almost 2013. So this was the power they were getting out of the fusion reaction with the old laser pulse. And when they switched over to the new laser pulse, they got much more yield. Right? In fact, for the first time, they got more energy out than they put in from the laser, which marks a major milestone in the path to ignition. Right? It was such important news that the team that did this ended up with a paper in Nature. Here's a second example. So renewable power, right? So the sun produces a bunch of power, and you'd like to be able to use that to replace the fuel you're using. The problem is, traditional storage would be batteries, which are expensive and don't work well, right? So another thing that people are looking at now is if you can store that energy in chemical bonds, it's a much better way to store the energy for transportation. You can store more energy in a given density. And so people are looking in particular at hydrogen, right? To create hydrogen gas for hydrogen fuel cells. One way that you can do that, which I find really fascinating, really, just the simplicity of it, if you just take a solar cell and you dunk it in water and expose it to hydrogen, or the sun rather, it will produce hydrogen gas. Right? So what happens is a photon comes in, strikes your semiconductor, an electron gets knocked up to the conduction band. If you have these metal catalysts on here, they eventually migrate over to the metal catalyst. They pick off a hydrogen atom from the oxygen, which eventually forms another hydrogen atom picked off from the water. And then you end up with hydrogen gas. Very neat way to create hydrogen fuel. The problem here is that you end up with a solution that's very acidic, and it eventually will eat away at your semiconductor. Right? So there's a problem with reliability. And that's what people at Livermore now study, again using MVAPICH to do these simulations. So there's a team looking at the interface between the water and the semiconductor using molecular dynamic simulations, and they're modeling different materials, trying to find materials that are more robust against this breakdown. Right? Again, this was a major success. These guys received the Department of Energy's Hydrogen Production Award last year for this work, all done on MVAPICH. Right, so let me recap those two examples. So You've got a major contribution to fusion science, major contribution to hydrogen fuel, and there's a third contribution actually that I didn't cover due to lack of time here, but additive manufacturing. You guys have heard of 3D laser printers. Another way that you can do additive manufacturing is you take a bunch of metal powder and you fill it in a box and zap it with a laser to melt the powder onto whatever object you're trying to create. Right? And we've got a team that's using simulation and uncertainty quantification in order to speed up qualification of parts made this way. Right, so this is all done with MVAPICH. I want to pause here because this is sort of the major point of this part of the talk. But to me, this is really amazing, right? Because this is just a small sample of the science that we're doing at Livermore. And Livermore is just one out of 2,500 organizations using MVAPICH software. Right? So, and all of these have had major and continue to have major impact on the world as we know it. Right? Like this is new science being done that will eventually help us in the future. Someday we get to fusion, or someday you're running your car on hydrogen fuel, MVAPICH had an impact on that. And to me, that's really amazing to be able to work on a project like you guys are doing that can impact so many people. Right? You guys should really be proud. Touchdown, Buckeyes. All right, so let me get into the second part of the talk real quick. This is I'm going to cover the future systems coming into Livermore, and then some of the future challenges that I see we need from MVAPICH. So the first one, this is a lot of words, but basically all of those red systems that I colored in earlier, we're eventually going to replace them. Right? We're going to start doing that in 2016, going through 2018. It takes about 3 years to cycle through them all. Each of those systems will last about 5 years. We don't know exactly what the network will be yet, although we do know it will be open fabrics, which means that MVAPICH stands a very good chance to be the primary API on all those systems. So we expect to be living with MVAPICH for some time yet to come. The other major system is our coral system, Sierra. Again, a lot of details here. I don't want to go into all this. Really, all I can say about Sierra is on this slide, so it's not here, I can't say it. But one of the things I want to highlight is the speed, right? So this will be a fast machine, 120 petaflops or so. I don't know where that's going to rank it when it finally comes in, but it's probably safe to say it'll be somewhere in the top 10. Right. Another item I'd like to highlight here is that we're going to have an SSD on each node. And then here, we're going to have Mellanox dual rail interconnect between nodes. We're going to be using NVIDIA chips. And then we have a power processor. And so a lot of the details you've seen in Dale's talk this morning will be on the system. And that leads into the first challenge, which is the MVAPICH team is already experts. Admittedly, this challenge is kind of selfish from Livermore community, but MVAPICH team, you guys are already experts in Mellanox and NVIDIA. If you can manage to port the power, it would be great to have MVAPICH running on Sierra when it hits the floor. And I think this is doable, and hopefully maybe we would have the world's fastest machine at that time. Not sure, but we would really love having MVAPICH there too. Challenge 2. So remember the SSD that I was showing. We're starting to see this in more and more of our systems, either in the form of SSD or non-volatile memory. And what that's driving some of our users to go for is what they want to do is load their whole data set in a sharded way across the whole cluster. But they want to access the data from different processes, right? And it's driving this need for asynchronous access to the data. And the way people are trying to implement that often comes down to spawning an asynchronous thread using MPI that's doing the message passing in the background of the main application, or sometimes in both cases, spawning a whole separate set of processes, which may be MPI processes, that are running alongside the MPI application. And so you have some file system service that's MPI-based, along with the application that's MPI-based, all running on the same nodes. And so we really need the capability of efficient thread multiple support and efficient non-blocking communication. right? And what I mean by, I guess I should clarify the non-blocking because that's an overloaded term, but, or rather I guess it would be blocking instead. But when a process is waiting for a message to come in, we would like it to not hold for the message, right? Because we have multiple processes on the node. We've overloaded the node with the application plus the service process. And if they're both competing for the core at the same time, it doesn't work very well. And so we would like to use blocking communication, but have it be more efficient than what it is today. The third challenge is to stabilize the API, or ADI. Our codes are something like 1 million lines of code. They have a whole lot of library dependencies. Anytime they have to rebuild or recompile, it takes literally a day for some, which is a major pain. And once they build it, when they recompile it, they have to test and verify it. And so anytime that MPI breaks API, that becomes a big pain for us, right? Because to get them to update from, say, MVAPICH 2.19 and MVAPICH 2.1 costs them a day or a few days of work. Right? And if there's nothing in there really that will gain them performance, they don't bother. And so we end up with codes scattered across this whole chain. We still have codes that are way back on MVAPICH 1. Dr. Panda showed that as end of life, but we're still using it. Right? So it's not dead yet. We have the latest in MVAPICH 1 if you need it. But if you could stabilize this API, it would make moving forward much, much easier for us. Avoid that recompile step. Challenge number 4, maybe you guys will argue with me on this a little bit, but part of the reason we still have people in MVAPICH 1 is because they tell me that it's still faster than MVAPICH 2. And I don't know exactly what they're doing, if that's the case, but that's the story I get. I haven't had time to check into it. And so if there are still bottlenecks in MVAPICH 2 where it's slower than MVAPICH 1, it would be great to knock those out too. Because I would really like to move everybody off of MVAPICH 1 so that we could agree that it's really dead. But I don't know why that is, but that's the story. And then the final challenge that I have is, and I brought this up again last year, but I would really like to see every linear term in MVAPICH eliminated. Right? So every linear data structure or every linear communication pattern knocked out. Because eventually, that's just not going to scale. One particular use case, and this may be the only place where it lives in MVAPICH anymore, is the communicator representation for groups. Right? And so this is one example of a very lightweight group representation that I've been working on. Right? And for example, if you represent a process group using just this simple range structure, you can split it in something close to logarithmic time, where it's logarithmic in the number of processes times the logarithmic of the group number that you have. Right? But this makes a big difference. So there's a leading P term here, which is your process count. This turns into a log G term here, the number of groups you have. And so at very large scale, like when P equals 1 million, and maybe your groups are 1,000, you end up with something that's 5 orders of magnitude difference. Right? So you can do this 100,000 times faster than 1 million processes. Right? Similarly, you can use a fuller group. You can go from this to something like this, which takes a little more space, but then that allows you to use some other log P collectives. And again, this representation compared to the existing linear representation, 100,000 times less memory. Right? So these are huge savings when you get up into the scale of like 1 million or something. And I think this is actually very exciting from a research angle because this is just one way of doing it. But there's a whole lot of ways you could implement distributed group representation. This is probably worth 2 or 3 papers at least. It's maybe a PhD. Because it's not trivial because you want it to still be efficient when you're sending messages. So if you don't have all the information locally, you have to do some remote lookup. Right? So it's not trivial to figure that out. Okay, so with that, let me recap just real quickly through the challenges. So number 1, port to power. 2, we like efficient thread multiple and efficient blocking communication. 3, eliminate the API breaks if possible, please. MVAPICH 2, make that faster than MVAPICH 1 or at least equal to. And then finally, eliminate every linear scaling term in the library. And then let me just summarize with this single slide, which gets to the 2 points that I had. One, to the MVAPICH team, thank you. Right. Second, please keep up the good work. Sincerely, your friend Science. Right. No, I'll end on that. And in case you didn't get the hidden theme, Buckeyes, national champions, 2015. I like this picture because even though Dr. Mand is holding the championship trophy, he's still not smiling.
Any questions for that? He always proves every year all these passions. I think he's always becoming creative and creative every year, so we'll see next year what you do. So I think just a response, I think several of these things, I think first few things are good, so try to go for them. So we can discuss the last one. Those kind of things are. One extra thing. Yeah. And this is exactly what it is not only our stack, anybody else stack also. As the system sizes are becoming larger and larger, and it's becoming really hard how you put these internal things. A lot of these things produced from the scientists and all the design 10 years back, 15 years back, so all those data structures are still there. So one has to totally rethink. We are entering an industry.